This is Cui Yu Yan. My student ID number is MAT1909397. In this video, I will show you the Bolzano-Weierstrass theorem. So now let's get started. What is Bolzano-Weierstrass theorem? Every bounded sequence has a convergent subsequence. The only condition we need to satisfy is bounded. This is a very concise statement, but maybe we cannot understand it very well. Let's look at this picture. This is a number axis. We discuss the sequence in this closed interval. Perhaps the sequence itself doesn't converge. We use white dots. The distribution is in a mess. But we can find several of these points. The color is yellow. They form a subsequence that is convergent. So how should we prove this conclusion? In other words, how do we find a convergent subsequence in such a bounded sequence? Professor Darren has taught us by using this way. In chapter 3, page 16, first he proved every sequence has a monotone subsequence. Then, by the theorem we learned before, since a sequence is bounded, its subsequence must also be bounded. By these two conclusions, monotone plus bounded, we can find a convergent subsequence. Then the proof is done. He explained in detail here that each sequence has a monotone subsequence. Let me briefly review this. If a point is a peak index, which means it seems to be a peak in the picture, which means whether left-hand side of this point is bigger or smaller than it doesn't matter. We only need to consider the point must always be bigger than all the points after it. Under this idea, there are only two cases: infinitely many peak indices and finitely many. If there are infinitely many indexes, all the peak index can form a subsequence. Easy to say, it is monotonically decreased. If finite many, look at this picture. There are only two peak indices, A3 and A5. Since A6 is not a peak index, there must exist a point after 6 which is bigger than it. Suppose it is A8. Similarly, maybe A9 is bigger than A8 and A11 is bigger than A9. Loop this operation. We can get a monotonically increasing sequence. Then prove them. So that every sequence must have a monotone subsequence. According to the concepts we mentioned earlier, we can get the Bolzano-Weierstrass theorem. Now I will introduce another method. Before beginning, let's review the nested interval theorem. For n belongs to big N, let an less than bn. Define set In as the closed interval from an to bn. Assume In plus 1 is the subinterval of In, which means the later closed interval is within the previous closed interval. This is the first condition. The other condition is when n goes to infinity, limit bn minus an equals to 0. Then the conclusion is there is exactly one point x that belongs to all an, and limit n goes to infinity an equals to bn equals to x. Let's come back to prove the Bolzano-Weierstrass theorem. We will use the nested interval theorem to gradually approximate the limit of this convergent subsequence, so that we can find it. Now let's look at this step-by-step analysis. Suppose that the sequence xn is bounded. What information can we get from bounded? It is bounded, then there exist some real numbers like a and b belongs to R such that xn is contained in the closed interval a, b. Noted a, b by I0. Now let's take the middle point of the interval, The first step is divided I0 into two equal-length intervals. Remember what interval a comma a plus b over 2 and a plus b over 2 comma b. Let's choose one interval of these two intervals. Remember, we're trying to find the limit point that the subsequence is convergent. So we take an interval which has infinitely many terms, called I1. And xn1 is a point in the interval. The length of I1 is b minus a over 2. Then divided in into two equal-length intervals. And we choose I2 to be the interval that contains infinitely many terms. It will work actually, because if the sequence is infinite and containing I1, we cannot divide it into two finite subsequences. And another thing I want to mention is that you don't necessarily divide it into two parts. It can also be like 3 parts or as many as you want. And actually, you don't need to divide it into equal-length interval, because whatever length interval is, you can always find an interval that contains infinitely many terms, right? So it's actually not strict the way you divide the interval. Anyway, now we get I2, and xn2 belongs to I2. There's an important thing that we make n2 bigger than n1. It can be done since I2 has infinitely many terms. Then we note the length of I2 is b minus a over 2 to the power of 2. If we continue this, in general case, we get ik belongs to ik minus 1 belongs to blah 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 until I1 at 0, and the length of ik is b minus a over 2 to the power of k. In contains infinitely many terms. We take xnk belongs to ik, and nk is bigger than nk minus 1. Based on the above analysis, we get a subsequence lying on a closed interval. This bounded sequence satisfies these three conditions. First, blah 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 is contained in ik minus 1 until blah 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 until I1 at 0. The second thing is when k goes to infinity, 2 to the power of k goes to 0, so that limit ik equals to 0. The absolute value of ik is the length of the interval. Then the first two conditions tell us that the subsequence satisfies the nested interval theorem. The third thing shows a very important math principle. That is to say, ik contained infinitely many terms in the original sequence, and xnk belongs to it, and nk is bigger than nk minus 1. By the nested interval theorem and squeeze theorem, we get when k goes to infinity, limit ak equals to bk equals to xnk, let it be c. Then we get every sequence has a convergent subsequence. In this method, we use nested interval theorem to approximate the interval containing such a subsequence, so that we can find the final convergence value. In the end, I want to say something that why I chose this theorem. We know the theory of limits is the basis of mathematical analysis, and the real number completeness theorem is also the basic theory of limit theory. It contains these 7 axioms. They can prove each other. So the Bolzano-Weierstrass theorem is very important. This is what I want to talk about in this video. Thank you for your listening.